Welcome to the post-JavaScript apocalypse. So what I'd like to do with you today is to share some ideas about what should be in the next language, the language that replaces JavaScript. Being an optimist, I believe there's got to be a next language. It doesn't stop here. That would just be sad. For our children, right, we need to figure out So the title of this talk is actually quite controversial. There are some experts who say that it should be the put JavaScript apocalypse. And others who say, no, it's the patch JavaScript apocalypse. And this confusion, post, put, and patch, is due to HTTP, the Hypertext Transport Protocol. It contains 3 commands for moving some information from one machine to another, and they are almost identical. But there are concerns that in some cases it makes a tremendous difference which one you use. That disaster could occur if you're using the wrong one. But it's not clear from looking at the names which one that should be and in what situations. So I see this as a problem. I think in a well-designed system, it should be obvious what the correct thing to do is, and you shouldn't have to struggle with these sorts of confusing things. So I look on this as a source of clutter. And clutter messes things up and actually makes things worse for us. We spend our lives accumulating stuff. It's been said that the one who dies with the most toys wins. And so we accumulate all this stuff, and we think the stuff that we have has value. And we think of it in terms of its cost of acquisition or maybe its cost of replacement. But actually, the more stuff you have, the more likely that the stuff is going to have negative value to you, that it's getting in the way, it's actually degrading the quality of your life. In some cases, you're looking for something that you know is in your stuff, and you cannot find it because there's all this other stuff in the way. So that extra stuff is reducing the value of the valuable stuff to 0, while adding no value of its own. In some cases, some of your stuff is literally destroying other stuff. You might have a pile of stuff, and the weight is destroying the stuff that's on the bottom, or maybe the stuff on the top is leaking down into the bottom, and it's making stuff worse. So there's this idea that you can improve the quality of your life by getting rid of some of your stuff. You identify the stuff that you don't need, and then you put it on eBay, or you sell it, or recycle it, or if it's worthless, you can get rid of it. If it's worthless, never mind. Anyway, thinking about clutter, it's a difficult thing to deal with. So I look to an authority. This is Komari, or Marie Kondo, a brilliant Japanese woman, maybe the world's biggest authority on organization. She teaches people how to organize their homes and places so that they can enjoy them better. And she teaches how to store and organize and fold and get rid of stuff. So one of the things she teaches is you go into a room and you take everything in the room out of the drawers, off the shelves, and put it in the middle of the floor. And then you pick up each item and you ask a question of each item. You say, to kimeku desu ka? Which means, do you throb? Do you vibrate? And if the thing speaks to you, then you keep it. There's some emotional connection with that thing that this is something you keep. And if it doesn't, then you think about getting rid of it. Now, when she teaches in English, she doesn't say throb or vibrate because it makes some people giggle, like that guy. So instead, she says, does it spark joy? Which is just delightful. So you pick up the thing, you ask, does this spark joy? And if it does, then you definitely keep it. And if not, you should consider getting rid of it. So I would like to apply her methodology to our programming systems, particularly to our programming languages. But spark joy doesn't work for us because everything sparks joy. We love all the clutter in our languages, and we can't get rid of it. And so sparking joy is not a sufficient criteria to get rid of the clutter in programming, much as we need to. So I want to show you some examples of clutter, things that we've lived with for a long time, perhaps so long that we can't even recognize that they're cluttered, and look at what we might do to clean them up. I'm going to start with ASCII, the American Standard Code for Information Interchange. ASCII is a really important code. It was for a long time the standard character set in the United States. It is still the first 128 characters of the Unicode set. So ASCII is still in use everywhere in the world. It contains two characters which are problematic, and they were both borrowed from typewriters. Space is from the space bar. It's a thing that allows the carriage on the typewriter to move forward one character space. And the other is tab. Tab was short for tabulator or tabulation. It was a key that when you pressed it would release the carriage, allowing it to move freely until it hit a mechanical obstruction called a tab stop. And the purpose of tab was to make it easier to type in columns of numbers. So we have both of these characters, and they can both be used in the preparation of computer programs. And it's not obvious which is better than the other. And so we use them both, which is itself a problem because there's some coding standards which are hostile to one another. It makes interoperability more difficult, sometimes makes formatting more difficult. But more than that, it's just a colossal waste of time, that this argument about tabs versus spaces just goes on, and there's no end because it doesn't appear that anybody's right. So there's a brilliant show on HBO called Silicon Valley. Has anybody seen Silicon Valley? It's the best show ever made about programming. You should all go out and buy HBO because HBO deserves to be compensated for making such a good show about what we do. No one else has done that. So, you also get, if you buy Silicon Valley, you also get Game of Thrones and Westworld and stuff like that. But this is the show you want. This is the good stuff. So it's about Richard Hendricks, who is a brilliant programmer, and his adventures in trying to start a software company in California. He's a brilliant guy. He works really hard. He's spending so much time trying to start his company that he doesn't have time to find a girlfriend. You might know the type, or you might be the type. Anyway, in season 3, he finally finds someone, and she's perfect for him. She's nice, she's smart, she's a programmer. She seems to like him for some reason, but she uses spaces instead of tabs. And it makes him crazy. And it turns out his affection for an invisible control character is greater than anything he could feel for another human being. And so he ends up destroying their relationship because he uses tabs. So, all the human misery that's caused by this conflict, tabs, spaces, what to do. So this is clutter, right? The two ways of doing things. I want to get uncluttered. I want to do it one way. So I want to get rid of one, just so that we stop all of the waste and all the confusion, all the craziness. Which one do you get rid of? There's only one that I can get rid of. I need the space. Space is an essential thing. It does things besides put things into columns. So I've got to get rid of tab. I don't need tab. And I know that's going to make some of you cry, but that's just how it is. Turns out tab does not spark joy. So now we know. So ASCII also provided two characters for quoting things, the single quote and the double quote. And JavaScript employs both. So in JavaScript, you can make a string with double quotes or single quotes, and they work exactly the same way. They just look different. And for a long time, I tried to figure out how to make sense out of that. That, for some purposes, I want to use a single quote. For other purposes, I want to use the double quote. And I thought it made sense, but I saw other people who had different conventions which also made equally as much sense, and they were incompatible, and it's like, there's no way to resolve this. So ultimately, I think we have to get rid of one. And the one that makes sense to get rid of is the single quote. And that's because it's also, it's because it's overloaded as the apostrophe. And so you're more likely to make mistakes using single quote than double quote, and I'm really down on mistakes. I'm trying to figure out how to be error-free as much as possible. So single quote does not spark joy. one of the most important things that ASCII did was come up with the way that we encode uppercase and lowercase. The original plan for ASCII was it was going to be a 6-bit character set that would give you 64 codes, which isn't very much. And in order to support lowercase, they're going to add 2 control characters for doing shifting. So you could shift one way and you get lowercase characters, and shift the other way and get uppercase characters. If they had followed through on this, then everything would be just A. We teach our kids that's an A, and there are 2 ways A can look, but they're both A. And that's how it would work. So we would distinguish uppercase and lowercase the same way we distinguish bold and weight, or italics, or underlining, or color, or anything else. But we didn't do that. And the reason we didn't was, at that time, they were shipping these character codes over teletype lines, and those lines were very noisy. And so it was not uncommon for a character to get a bit or more damaged, and it would arrive garbled. And their concern was that if a shift character gets garbled, then the rest of the message is going to look stupid. It turns into shouting and stuff, and they didn't want to do that. So to avoid that particular error, they decided to increase the size of ASCII to 7 bits. That gave them 128 characters, and then it became possible to give each of the lowercase characters a unique code. And in doing so, they invented case sensitivity, which had never existed prior to that as a concept. And that is a source of bugs for us today. Some things want to be case sensitive because it's faster, and some things want to be case insensitive because it's correct. And boom, so that happened. I can't fix that. It's too late for that one. JavaScript gives us let and var, at least since ES6. They both do the same thing. They both declare a variable and a function, which you definitely want to be doing. But it's confusing having 2 of them. And I've seen people argue, well, you should use var in this case and let in that case. And I go, no, you don't want to be doing that. It's just confusing. So we want to be using just one of them. And I think the one we want to be using is let. And the reason I prefer let is the Java guys don't get as confused if you're using let, because let respects block scope. We don't need block scope, but the Java guys don't understand function scope, and so we should do that. Now, the problem with this recommendation is it does not work for IE, because in IE, let doesn't exist, so it's a syntax error. So my advice is stop IE, right? No more IE. Even Microsoft doesn't want it anymore. They want us to move to Edge. I think they're exactly right. Let's stop doing that. ES6 also introduced const, which is like let, except you cannot modify that variable anymore, or you can't replace that variable with another value, which is a good thing. So generally, when given a choice, I would prefer to use const than let. JavaScript gives us 2 bottom values, null and undefined. There's an argument in the language design community, should a language even have bottom values? But there's nobody who thinks you should have 2 of them. And due to some accident, JavaScript has 2 of them. And they are not interchangeable. For many purposes, they work the same, but there are some specific cases where they're not. And when you have things which look to be the same but aren't actually the same for no good reason, that creates confusion and bugs, and that's bad. So I want to get rid of one of them. And usually when I have a choice between 2 words, I want to go with the shorter one. But not this time. This time I'm going with undefined and getting rid of null. For one thing, null has the type of problem. Type of null is not null. It's object, which is horribly wrong. And if you never use null, then you don't care. So that can stay broken and nothing breaks. Undefined is not a good word. It's really confusing, but we're kind of stuck with that. Now, the idea of null as a special kind of pointer, as a standard feature of programming languages, is due to Tony Hoare, who's a brilliant British programmer. Everybody know Hoare? Yeah, they should teach history here. I mean, it's important stuff. Anyway, he came up with that idea, and he now regrets it. He calls it a billion-dollar mistake. I don't know why he didn't call it a billion-pound mistake, but he called it a billion-dollar mistake. And he came up with that figure by estimating the accumulated cost of all of the null pointer exceptions that he caused. So, it shouldn't be a special kind of pointer that fails. It should have been something else. And what I think it should have been is an immutable empty object, in the sense of a JavaScript object, where it's a thing and you can't store anything into it. If you try to store anything into it, that'll throw an exception. And if you try to extract anything from it, you'll just get null again, which would be fine. And it could be implemented in a JavaScript-like language very simply. We just create a constant which contains a frozen empty object that doesn't inherit anything. So, in fact, for some purposes, instead of using undefined, you might actually want to create your own thing, give it another similar confusing name, like maybe nil or none or something like that, or even empty, and do that with it. Now, functional programming is becoming really, really important now, finally, we started doing functional programming in the very late 40s, early 50s, and it's just kind of now getting to the mainstream. JavaScript there are two senses of a functional language. A functional language is a language that uses functions. There are two senses of what functions mean. There's functions as what we do in programming, like a JavaScript function. There's also the idea of a mathematical function, and that's sometimes called pure functional programming. A mathematical function isn't really about computation, it's about mapping. A pure function will map values from one thing to another. And the process of mapping doesn't allow for side effects or any other stuff going on. It's just one thing. So in a mathematical function, in a pure function, a given input will always yield exactly the same output. And they allow for no mutation, no side effects, nothing else is going on, just the mapping of one value to another. And that turns out to be a really cool thing. You get some nice benefits from that. One of them is testability. Programs written this way become much easier to test because once you've shown that a function returns the correct value, you're done. Nothing else can ever cause that function to now misfire or behave incorrectly. So that significantly simplifies the process of testing. An even better benefit is in composability, that when functions are pure, you can string them together and compose them in really interesting ways. And that becomes a very, very effective way of programming, much more efficient. Maybe the best benefit is parallelism. The problem we have with threads in a crappy language like Java is that we're trying to do read, modify, write of shared memory. And that is an inherently dangerous thing. If you do it incorrectly, it means you get races, which are horrendously difficult bugs to find and correct. The way you mitigate that is by locking, which slows programs down profoundly. And if you're just doing stuff with pure functions, you can run full speed. That the functions never read, modify, write because they're not allowed to mutate. They can't have side effects, so they just run and run and run, and there's nothing to slow them down. So the fastest programs that we can write are probably going to be functions that are pure, which is, again, a really good reason for doing it. So we can convert JavaScript into a pure functional programming language. And the way we do that is by removing the impurities. So we'll start by removing the date function, because every time you call the date function, you get a different value. And that's not a mathematically pure function, so we're going to get rid of that. We have to get rid of the random function. Same reason. Every time you call random, you get a different number. That's not pure, so that's got to go. We have to take out the delete operator because it can modify an object. We have to take out object.assign and similar functions because they will attempt to modify an object. We can't allow for modification. Array.splice and all the other array methods, we have to take those out as well. We can keep slice because it makes a copy of an array, so that one's good. But the ones that modify an array, we have to get rid of. Array.sort could have been a pure function, but it was implemented incorrectly and it is not. So sadly, we have to get rid of that one. The regular expression exec function wants to modify the regular expression object, so sadly that's got to go. Assignment, right? The equal sign, that goes. The var statement, if you don't have assignment, you don't need variables. We have to get rid of let as well, but we can keep const. Const still has a role. So we could call a function and put its return value in a const, and then we could use that value in multiple places in the remainder of the function. That's cool. That's pure. We can do that. For statement, that wants to modify an induction variable. We can't be modifying, so for's got to go. In fact, probably loops in general are probably going to go. Users. It turns out, every time the user does something, it could be different. Users are surprisingly non-mathematical, so they're going to have to go. And the network, yeah, every time you get something from the network, you could get something else. So that's not pure, so network's got to go. So a absolutely pure functional programming model doesn't make any sense because the universe is mutating, and unless our programs can deal with the mutation of the universe, they're limited in how useful they can be. But purity is still really valuable. And so we need to figure out the models which allow us to be as pure as we can while still permitting enough impurity to actually allow us to get work done. One of the new features in ES6 is generators, something that I think shouldn't have happened just because it's unnecessary. A generator is a function which every time you call it will return a new value. So generators are not pure, but they're still very useful. And it turns out using higher order functions, you can get generators without the weird special syntax with the yield and the asterisk. So this, if you need generators, this is how I think you should make them. So we've got a factory function, which is the thing that makes generators, and it can take arguments. And the variables of the factory function become the state variables of the generator. Then the factory returns a function, which is the generator function, and each time it's called, it will compute a new value and update the state variables that are in the closure of the outer function and return the value. This is a really straightforward pattern. It's really easy to write. So here's an example. This is the element generator, which will receive an array and return a generator which will return each individual element of that array. Really straightforward. I like this better than the equivalent thing you would get by using the function star syntax. Callbacks are a really important mechanism for dealing with asynchronicity and other patterns. And there's a question, callbacks are also used in continuation passing style. It's a really powerful way of expressing programs. And so it means that a function not only gets its normal arguments, it also gets a special argument, which is the function to call with the result. And there are two places where you could put it. You could make it the first parameter, or you could make it the last parameter. And up until now, it's been up to you. Do you want to put it in the first position, or you want to put it in the last position? And since you have a choice, we will, apparently at random, choose one, and then we will argue about it. And that makes interoperability much harder, because if I'm putting them first and you're putting them last and our code has to work together, it's just annoying. So it'd be good if we could figure out what the right answer is. And it turns out ES6 tells us what the right answer is, that they want to be first. And the reason they want to be first is we now have the ellipsis operator, which is my second most favorite feature in ES6, which says take all of the rest of the arguments and make an array and stick them in there and pass that as the last argument. And that only works in the last position, which means if we want a callback, the callback really needs to be in the first position. So those of you who are putting it in the last, yeah, you got some work to do. Promises were added in ES6 because W3C was threatening to standardize them, and ECMA said, no, you can't do that. You're going to screw it all up. So basically, ECMA took W3C's spec and published it, which didn't really prevent anything from getting screwed up. So we got that. The original purpose of promises was not to provide for asynchronicity, but that's the major function for it now. And I don't think they do all that good of a job. They actually do work, and they're much better than doing nested callbacks, but I think we could do better. For example, I developed a library called ourqueue, which is sort of a cryptic name. I kind of regret that now, but I was feeling very terse the day I named it, which provides for a much nicer composable way of dealing with asynchronicity, particularly for the kinds of things you would do in a server, where I want to do these things as a sequence, and I want to do these things in parallel, and I want them to all compose together and be good in an asynchronous way. ourqueue does that. So we get really emotional about our syntax. We love the syntax. And it turns out syntax really doesn't matter, but we don't know that. We love it. And syntax has more to do with fashion than with functionality. And so I want to look at a few examples of syntax through the ages. So we'll start with Fortran. Fortran 4 was my first language, and this is how we wrote an if statement in Fortran. In Fortran, lowercase hadn't been discovered yet when Fortran was made, so everything was all in uppercase. In Fortran, spaces were not significant, so that if you said if space A, that looked exactly the same to the compiler as IFA. And so when they designed the if statement, they came up with the idea of using the parentheses to separate the keyword from the condition, because spaces couldn't do that in Fortran. And similarly, they used the closing paren to separate the end of the condition from the consequence. BCPL was one of the first good parts languages. It was modeled after an earlier language called CPL, which I think was designed not too far from here. And it was the first curly brace language, really nice-looking language, and I think they got it basically right. So in BCPL, the parentheses around the condition were optional, and the curly braces around the consequence were required, which is really, really smart. Unfortunately, when the B language and then C and then Java and then JavaScript, in all of those languages, they got it wrong again. They went back to the Fortran convention. So they required the parentheses around the condition, which really doesn't accomplish anything, and they allowed for leaving the curly braces off of the consequence, which turns out to be a problem. That it's really easy to write an if statement which appears to control several statements, but it only controls the first. Very common source of errors. And because of that, I recommend always put the curly braces in every time. On every if and every else, always put the curly braces in, because it increases the likelihood that somebody, including future you, can improve that program without breaking it. Algol 60 was a brilliant language designed by a committee. It's very rare for a good language to be designed by a committee. That was the one example. And they did such a brilliant job, they decided, let's do it again. So they convened a second committee, and they developed Algol 68, which unfortunately was a mess and very cluttered and didn't get well adopted. But I really liked their if statement. I think Dijkstra suggested the syntax, and I think it's just lovely. So instead of having the curly braces or blocks or anything like that, they just have a phi statement which balances the if. And the nice thing about this is that when you look at a program, you've got lots of curly braces, and the curly braces represent the end of blocks, the end of functions, the end of object literals. And sometimes it's hard to know when you look at a curly brace, who are you closing? And a lot of what we're closing is ifs, and if the if is using a different convention, then it's much easier to read the program. It's much clearer what's being delimited, and it's easier to write programs that are correct, which is really nice. But I think we can improve a little bit on this one. So this is my suggestion for if there are any language designers in the house. I would like to see this in the next language. So I think Python had the right idea about respecting line breaks, that where a line break is significant, it's probably significant to us as well as to the compiler. So let's just hard code that into the language. That being the case, I don't need the then, so we can take that out. And there's a lovely little language called Rebel, which uses colon as its assignment operator, which I think is just so nice. So I would shorten it a little bit more. I don't think I'd want to go much farther than that, because if you get too cryptic, then you start to be APL, and we don't want to go there. But I like the idea of trying to be as minimal as we can in our syntax without losing clarity. And I think this might be a way to go. So talking about not clarity, so we've got the try statement. Exception handling is an important idea because we don't want to have, after every function call, to query the result and ask, did you fail or not? Because that really slows things down. So the idea was we'll have exception handling so that we don't have to do that testing. So this is the way you would write a try-catch statement in Java or some other crappy language. They look like this. And it's big, there's a lot of stuff in it. So the interesting bit is the code that might fail. That's the stuff that we're trying to protect, that we don't want to have to query everything that happens within that block, and then there's everything else. So the finally bit is there because Java did not have functions. And basically what finally wants to do is do this stuff no matter how we exit from the try. And the way the Java virtual machine implements finally is with a subroutine call. There's a subroutine call and return which is in the language specifically for try-catch, or for finally. And they did it that way because they didn't have functions, which would have been the correct way to do it. And so since we have functions in JavaScript, we don't need finally. So I see finally as just being noise. Then we've got all of these catch clauses. So what's going on there? The catch clauses are all there because of a failure in the type system. So often a particular function or method might have multiple kinds of things that might happen. There's one that is most likely to happen, but there's another thing which is expected to happen sometimes. Like maybe you get to the end of something and that's going to be a different kind of response. But that's not the same as failure, which is what exceptions were intended to catch. And so because the type system doesn't allow a single method to return things of multiple types, it will instead use the catch clause as an alternate control flow in order to sneak stuff through. So it's a misuse of the exception system, again, motivated by problems in the type system. And so basically what you get is code that looks like the Fortran assigned goto, which is quite an awful thing, where some other piece of code will determine what our path is going to be through this stuff, which is quite awful. Now JavaScript, because it has a superior type system, basically it doesn't care, allows you to send whatever you need back, and so you don't need to overload the exception system to handle your correct result. So in JavaScript, it gets much easier. So basically, you try plan A, and if that works, you're great. And if it doesn't, then you'll go to plan B. You don't even care why it failed. It shouldn't matter why it failed. You just know it didn't work, so let's do the other thing. And so that's much better. So this is an example of how having a loose type system allows you to write better code. Another example of Java's dilemma with types is in the index of operator, or index of method, So it wants to return the character position at which we find a particular substring. But there's a chance that it might not find it. And so what they should have returned would have been null, or something which indicates whatever we wanted to return, we got this instead. But they couldn't because null was not compatible with int. So instead they came up with -1. And the expectation is you have to remember that -1 is this weird thing. The problem is that for some of the string methods, -1 is meaningful. Like on slice, it means the last character of the string. And so you can get into trouble if you're not aware of this weird stuff that's going to happen. So let's talk some more about types and ints. So what is the type of the result of adding two int32 together? Anybody know? In truth. What is the true answer? Well, I didn't think that would stump everybody, but the answer is int33. int33, because the result of adding two 32-bit ints together is you could get one that's 1 bit more. Java and many other languages get this wrong. They think it's int32, which means that if that happens, if you get an int33 answer, the most important of all of those bits gets thrown away without any notification, and programs go wildly wrong. So let's look at another one. What is the type of int32 times int32? Any guesses? No? Well, okay. The answer is int63. int63. But Java thinks it's int32, so it's wildly wrong. It's going to throw away a whole lot of bits, which again is a source of terrible errors. So there's this idea that our type systems are helping us, that they're preventing us from making mistakes, but in fact, we can show that the type system is causing mistakes. Here's a famous example, and this is true of almost all of our modern languages today. 0.1 plus 0.2 is not equal to 0.3. And I think this is shocking. I think this is inexcusable. But it gets worse than that. It breaks the associativity. So 0.1 plus 0.2 plus 0.3 is not equal to 0.1 plus 0.2 plus 0.3. Associativity works if, in computer arithmetic, if the two operands are represented exactly and if their result can be represented exactly. And if not, then associativity will give you different answers, will break. And the problem is, in these languages, including JavaScript, 0.1 cannot be represented exactly, even though it has a very simple, trivial decimal representation. And it's because we're using binary floating point. And binary floating point was something that made a lot of sense in the 50s, but doesn't make sense anymore, but we can't stop doing it. So I recommend that we stop doing it. And this is how I recommend that we do it. This is a new number type called DEX64. It's stored in a 64-bit word. It contains two portions, a 56-bit coefficient, which is just an integer that's shifted over 8 spots, and an 8-bit exponent. And the value of the number is the coefficient times 10 raised to the exponent. This was inspired by a representation that was used in the EDSAC. Anybody know EDSAC? Well, they should teach you guys more history. EDSAC was one of the first von Neumann machines. It was built not far from here. It was brilliant and wonderful, and you should know this. This is important stuff. Anyway, I propose modernizing that idea and bringing it back. And when we do this, then 0.1 plus 0.2 will be 0.3. One of the nice things about this representation is that in a hardware implementation, adding any two numbers with the same exponent, for example, integers, will execute in one cycle. And being able to do that means the advantage for having ints goes away. And so there's no reason to have ints anymore. That I propose that all future languages or all future application languages use only this number type. That having a single number type in the system means that you cannot make a bug by choosing the wrong number type, which is a good thing to have. So if you're curious about it, for example, if you're an amateur language designer and you'd like to try it out, there's a reference implementation in x64 assembly language. It's on GitHub. You can go get that. So let's talk some more about numbers. What is 0 divided by 0? So it's actually a very complicated question. There are a lot of answers to this question. Most mathematicians would say it's undefined. Not in the crazy sense of JavaScript's undefined, meaning it's meaningless. It doesn't make sense to talk about 0 divided by 0. It's just not possible. You know, don't say that anymore. It's not a thing. Except in computation, things will happen because someone will divide 0 by 0 anyway. So the machine has to have some defined behavior. So one possible answer is the machine should catch fire, because it shouldn't happen, so it shouldn't matter that the machine catches fire. We know that that's actually not a good thing to do. Another possibility is it should be nan, because that's a representation of something that's meaningless, although nan has much more meaning than meaningless has, but that's something we could say. Another answer is it should be 0, because 0 divided by anything should be 0. And in fact, for a lot of business applications, that is the preferred answer. Or it could be 1, because n over n is 1, right? Sometimes. I once programmed a mainframe where the answer was 2. It was exactly 2. It was a machine designed by Seymour Cray, who was the greatest computer maker who ever lived. And when you divided 0 by 0 with a floating point divide, you got 2. And I'm sure somebody at Control Data said, hey, Seymour, we checked this out and we get a 2 here. And he said, I'm not going to fix it. Because if I fix it, it means it's going to add more circuitry to what is already a very complex circuit. And I don't want to do that because it's going to make it more expensive. And it's going to add 1 cycle to the divide time, which will penalize all of the correct uses of division. And I want the machine to be very fast for doing the correct things, and only an idiot would try to divide 0 by 0. So I'm not going to fix it. And they got away with it. And as far as I know, I'm the only person who ever divided 0 by 0 on that machine. And you know, I survived. It didn't catch fire or anything. It was good. So the reason I went through that was I'm actually more concerned with this case. What happens when you multiply 0 by n? What should the answer to that be? I think the answer should be 0, regardless of the value of n. And compiler writers used to think so too. So if a compiler saw that 0 is going to be one of the factors of a multiply, and if the other operand is pure, meaning it has no side effects, we do not even need to evaluate it. We don't even need to generate the code for looking at it. We just return 0, we're done. And so the compiler goes faster, and the program runs faster, and everything is great. That turned out to be an error when the new IEEE floating point standard came out, because it said that if n is nan, then the answer has to be nan. I think this was a mistake, that it made things go slower in all cases to protect us from something that shouldn't have mattered. And in fact, there's some programs that really want to be using 0 times n in a meaningful way. So who writes code like that? Generally not humans, but code generators do, and macro processors, partial evaluators, those sorts of programs can make very good use of 0 times n. Also, on modern CPUs, one of the slowest things we can do now is a conditional jump. And sometimes, instead of coding a conditional jump, we can encode multiply something by something that might be a 0 or a 1. and that multiplication can be significantly faster. In some cases, doing 2 multiplications and an add of either 0 or 1 or 1 and 0, that's faster than doing the conditional jump. And I don't see any benefit that comes from getting a nan out of that. So I would propose in the next language that all of these forms return 0, just because they allow us to get a little bit more performance, and we really don't benefit at all from getting nan from any of these. So modern languages have reserved words. And the reason they have reserved words is it made it easier for compiler writers at a time when memories were very small. For example, a lot of the early Unix work, the early B and C work was done on I think it was a PDP-7 that had like 16K of RAM, really tiny machine. And they got a compiler to run in there, which is pretty amazing. And one of the tricks they used in order to get that to happen was they reserved a lot of words in the language, so that the compiler didn't have to figure out, does this if mean a variable name, or does it if mean something that's a statement form? And we're still doing that. You know, our memories have gotten much bigger. We have much better tools for writing compilers, but we're still using this constraint. The reason it matters is it's a hazard for programmers, because it means you need to be aware of all the reserved words in the language, even if you don't use those words. Because if you name a parameter or a variable after one of those, then your program's going to fail, and that's a bad thing. And it's bad for language maintainers, because they want to introduce new features into the language, but if there's a likelihood that anybody else has ever created a variable with that name, then they're going to create failure, and they're trying hard not to cause things to fail. So often what they'll do is they'll come up with unpopular names. For example, when exception handling was first being proposed, the way we would cause an exception to happen was through a raise command. We're going to raise an exception, the way you might want to raise an issue or something. We'll raise an exception. It also has sort of a hardware connotation. We're going to raise the exception line. But they couldn't use the word raise because someone had used it to raise something to a power, and that would cause breakage. So they looked for a word that means something like raise that nobody was using. And in desperation, they came up with throw. Now, most of you have never seen anything except throw, so it probably looks natural to you now because you've never experienced anything else, but it was not the ideal choice. So I propose that in the next language, we do it better. So in any function, a word may be used as a language keyword or as the name of a variable or a parameter or something, but not both. So the programmer gets to decide. So if you want a variable called if, you can have a variable called if, but you can't also have an if in that function. So this is good for programmers because you won't trip over features you don't use. If you're not aware that double, for example, is a reserved word, doesn't matter. And it's good for language maintainers because they can introduce new features without breaking existing programs. Existing programs will be using the new feature already as a variable. They're not going to be using the new feature. Nothing breaks. Another thing we argue about a lot is how do we represent variables or identifiers that contain more than one word? And we do this a lot. And we have two conventions for how you do that. We've got Camelcase and we've got Underbar. And we argue about it all the time. And there's one argument that says, use whichever one makes you happy, which is not good because when code is written using both conventions, it just looks stupid. And so we don't want to do that. But we can't agree on what the correct thing is. And so we just argue and argue. And I've heard really ridiculous arguments on both sides of it. For example, I heard really smart people say, Camelcase is better because it wastes so much time when you have to go shift up to the underbar, which is just nuts. So the reason we can't agree is because everybody is wrong. The correct answer is names with spaces. That's the correct way to do it. And We didn't do this in the old days, again, because there was only a tiny amount of memory, and it made it harder to write the compilers. But those constraints have been gone for many decades now, so I think it's time to reconsider how we write our programs. So I propose this rule in the next language. A name is composed of one or more text atoms, which are separated by spaces, and starting with an initial text atom, we combine them to make the longest name that makes sense, that matches something that's been defined in the scope. And if a name makes sense, if it doesn't make sense, then we just take the first token and then we start again on the next one. Really easy to implement, and I think it'll give us much nicer looking programs. Something else I'd like to see in the next language would be programming by contract. This is something that the Eiffel language did, which was brilliant. That you could have a function, and in that function you have a little preamble or a requirements section which says, these things must be true when we start this function. And it could be just a series of conditions. And then at the end of the function you can also say, and when we leave this function, these things must also be true. And you can get these preconditions and postconditions provide very nice documentation for the thing. It makes it extremely explicit what the assumptions of the function are. So looking at that, it's much easier to use it correctly. Even more important, that stuff can be executed automatically. So we can turn on a mode which says that stuff turns into code. And so we now have diagnostic checking running in the program. We can even leave it on in production because it's pretty fast and we get much higher reliability. And it gives us much better information than types do as to what the expectations of a function are. So unfortunately, it fell out of fashion, but it shouldn't have. It's really good stuff. I hope we have that come back. I hope that the next language does a much better job of security, because as the world is becoming more distributed and we've got programs running everywhere and more of the value of our lives are online, it's really important that our programming languages not undermine us, that they respect the importance of our relationships and help us to defend them. So I don't have any specific suggestions, but I think it's something we need to be concerned with. And when we look at the next language, we should look much harder at its security implications, because in the past, we have never done that. And finally, we should be dealing with distribution, because that's how we're programming now. Going all the way back to Fortran, we've been doing sequential programming, where a program does one damn thing after another. And that's not how we do stuff anymore. That we now have multi-cores, and we expect stuff to be running concurrently on all of the cores. And even more than that, we now have the internet and the clouds and all of that other stuff. And so a program is expected to run not just in one machine, in one memory space, but in n memory spaces simultaneously. And providing for the coordination and distribution of all of that stuff, that should be built into the next language, because that stuff is really important. Mostly what we get in our languages are new syntax on the Fortran model, which is nice, but it's not sufficient. The next language should take us much farther. There's another paradigm we need to move into. And I'd like to find that in the language that replaces JavaScript. So that's the end. So I just want to leave you with a warning. Be careful out there, because the web is cluttered and full of errors. Thank you.